Introduction. Look at these numbers. Do you know what do we call these numbers? These are the real numbers. Teacher, is an irrational number is also a real number? Yes, an irrational number is also a real number. A rational number or an irrational number is called a real number. Today we will learn more about rational as well as irrational numbers. Objectives. At the end of this lesson, you will be able to define irrational numbers, show whether the number is irrational or not, explain rational numbers and their decimal expansions, convert the rational numbers into decimal expansion. Revisiting irrational numbers. We know that rationals and irrationals together made up the real numbers. A number S is called irrational if it cannot be written in the form P upon Q, where P and Q are integers and Q is not equal to 0. Irrational means not rational. The most famous irrational number is square root 2. Other examples are pi, which is equal to 3.141592 and 0.1011011110 1110 and so on, etc. Theorem related to irrational numbers. Theorem. Let P be a prime number. If P divides A square, then P divides A, where A is positive integer. Let us prove this theorem. Proof. Here we will firstly find the prime factorization of A. That is, A is equal to P1, P2, so on till Pn, where P1, P2, and so on till Pn are primes, not necessarily distinct. Therefore, A square is equal to P1, P2, and so on till Pn. P1, P2, and so on till Pn is equal to P1 square, P2 square, and so on till Pn square. Now, as it is given that P divides A square, therefore, from the fundamental theorem of arithmetic, we can say that P is one of the prime factors of A square. Also, we realize that the only prime factors of A square are P1, P2, and so on, Pn. So, P is one of the P1, P2, so on till Pn. Now, since A is equal to P1, P2, so on till Pn, we can say that P divides A. Theorem. Let us now prove that square root 2 is irrational. Suppose square root 2 is rational. That means it can be written as the ratio of two integers P and Q. Square root 2 is equal to P upon Q, which is equation 1, where we may assume that P and Q have no common factors. If there are any common factors, we cancel them in the numerator and denominator. Squaring in 1 on both sides gives 2 is equal to P square upon Q square, equation 2, which implies P square is equal to 2Q square, equation 3. Thus, P square is even. The only way this can be true is that P itself is even. But then P square is actually divisible by 4, hence Q is square, and therefore Q must be even. So P and Q are both even, which is a contradiction to our assumption that they have no common factors. The square root of 2 cannot be rational. Example. Let us solve an example now. Prove that 1 upon square root 2 is irrational. Proof. Let us assume to the contrary that 1 upon square root 2 is rational. That is, we can find coprime A and B where B is not equal to 0 such that 1 upon square root 2 is equal to A upon B. Therefore, B upon A is equal to square root 2 or square root 2 is equal to B upon A. Since A, B are integers, we get B upon A is rational and so square root 2 is rational. But this contradicts the fact that square root 2 is irrational. This contradiction has arisen because our incorrect assumption that square root 2 is rational. Example. Prove that 7 square root 5 is irrational. Let us assume to the contrary that 7 square root 5 is rational. That is, we can find coprime A and B, where B is not equal to 0 such that 7 square root 5 is equal to A upon B. Therefore, A upon B upon 7 is equal to square root 5, or square root 5 is equal to A upon B upon 7. Since A, B are integers, we get A upon B upon 7 is rational, and so square root 5 is rational. But this contradicts the fact that square root 5 is irrational. This contradiction has arisen because of our incorrect assumption that 7 square root 5 is rational. Revisiting rational numbers and their decimal expansions. As you may remember from school, rational numbers have a terminating or eventually repeating periodic decimal expansion, whereas irrational numbers don't. So, for example, 0.123, 123, 123, 123, and so on, with 123 repeating forever is rational. In fact, it is equal to 41 upon 333. Whereas something like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on, which will never repeat, is irrational. Terminating decimal. If the number of digits after decimal is finite, is a terminating decimal. Example, 2.57, 3.1925, 0.333. Non-terminating decimal. If the numbers of digits after decimal are infinite, then it is a non-terminating decimal. Theorem related to rational numbers and their decimal expansions. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form p upon q, where p and q are coprime and the prime factorization of q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. For example, 0.1837 can also be written as, we know that the rational number p upon q can be converted into decimal representation by using long division method by dividing p by q. Look at this example now. Here we can see that a rational number of the form p upon q, where q is of the form 2 raised to the power n, 5 raised to the power m, is converted to an equivalent rational number of the form a upon b, where b is a power of 10. The decimal expansion of such a rational number terminates. One more thing to note is that a terminating decimal can also be thought of as being followed by an infinite sequence of zeros. So in this sense, even terminating decimals are actually periodic. Theorem. Let x is equal to p upon q be a rational number such that the prime factorization of q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let us solve an example. Without actually performing the long division, state whether the following rational number will have a terminating decimal expansion or a non-terminating repeating decimal expansion. 13 upon 3125. We can write it as 13 upon 3125 is equal to 13 upon 5 raised to the power 5. Here q is 5 raised to the power 5, which is of the form 2 raised to the power n, 5 raised to the power m, n is equal to 0, m is equal to 5. So the rational number 13 upon 3125 has a terminating decimal expansion. Let x equals p upon q be a rational number such that the prime factorization of q is not of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, recurring. Let us now write the decimal expansion of 17 upon 8. Similarly, decimal expansion of 15 upon 1600 is 0.009375. Did you know? The word algorithm comes from the name of the 9th century Persian mathematician Al-Khwarizmi. Even the word algebra is derived from a book he wrote called Hisab al-Jabr wa al-Muqabala. Summary. Let us summarize what we have learned. Let x be a rational number whose decimal expansion terminates. Then we can express x in the form p upon q, where p and q are co-prime, and the prime factorization of q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Let x is equal to p upon q be a rational number such that the prime factorization of q is of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let x equals p upon q be a rational number such that the prime factorization of q is not of the form 2 raised to the power n, 5 raised to the power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating.